All right. This is In Search of Certainty. This is our sixth podcast. I think this morning we're going to try to attempt to look at the history of configuration management with my good friend Mark Burgess.
Hi, everybody. Hey, John.
Good. So I was thinking we ended the last podcast. We were talking a little bit about kind of promise theory, but I thought maybe it would be really interesting to kind of dive into, I would say, history of configuration management as it begins at the end of the 1980s and early 90s. And what was funny for me though is I thought, well, I was going to have to do a minor apology that this isn't going to be our normal physics and science. And as I was going back and kind of reviewing your book In Search of Certainty about how your ideas, and I was like, oh well, actually it's going to be perfect because it's kind of. But I thought maybe I'd start with just my perspective on, as we were kind of coming out of the 1980s into 1990s, what I've traditionally called first generation configuration management. Maybe prior to first generation was just scripts, right? But there was, products like Tivoli. I did a lot of work on that, and then, there were a couple other kind of products around the same time that nobody's even heard of now anymore. And then there was kind of kind of an edge of, Blade Logic and those things. But in general, the ones that I worked with had the thing I think that were unique about them is they were kind of born on how to really add software to a personal computer. Eventually they added software to servers, but there was this concept of kind of incrementally slapping on this, slap on that, slap on that. The reason I say slap on because it was really kind of an ordered list of install package this, install package that. It had some logic of if this failed, don't go any further. But one of the key points it really didn't have. I mean, it had it had macro like DSLs, but had no sense of kind of intent or a state of a and I know these days we're kind of moving away from the idea of a node, in some places, but it really had no at the time sense of this is a node, like this was a particular um, object type that things should actually be put together to make work. And then clearly it didn't have some of the ideas that I think you uniquely introduced to our industry, which is the convergence and desire state convergence and idempotency.
Well, actually, there's another sort of chapter of that which we often forget because on the server side of things, which is certainly where I started out, there was very little technology going on. Um, um, to formalize these things. But in the world of network management, there were these initiatives that go back further, like SNMP, of course, the OSI management model, the Common Information Model, SIM, um, the what's it called, DMTF frameworks, which were much more rooted in programming and object-oriented infrastructure than anything that was going on on the server side at the time. And we tend to forget about those because they were so far away from anything useful for configuring servers because, of course, they had no um, notion of state.
It's interesting though. I didn't realize because I'd forgotten about that. I had actually done a lot of work in that area myself because actually, so like I said, I did a lot of work with Tivoli, and in the early days, Tivoli was very innovative. Like so, like at the time, like the way they put, in fact, they built their whole architecture on, basically a pre-version one Corber, right? Like so, this was and the idea of using that for kind of an overarching framework to manage systems. That was pretty clever, but they got heavily involved in the DMTF as well. And the early incarnations of DMTF were things like, how you describe what was on a machine. They had these things called MIF files, and I get very excited about this because there's a lost art that I think where you took the industry is like it had to go. It was very interesting, and I want to spend a lot of time talking about that. But I think there's the piece that frustrates the heck out of me is there was kind of a DMTF kind of first rev, and then a second rev was about something where they called application management specification. And I don't know if you ever worked with this, but we're still not back to this today. So, the original idea was describing an inventory of what's on a machine. That was kind of MIF files, right? And then they went to these MOF files, and they were object formats and all that. But at the same time, they really, the original acronym from DMTF was Desktop Management Task Force. When they went to the second generation, it became Distributed Management Task Force. And basically, one of the specifications that's been just absolutely lost is something called Application Management Specification, where, get this, developers could actually encode kind of the inventory, the events, how they wanted monitored, how it would be distributed. It was an abstraction. And so it was like these MOF formats that a developer could actually, as they're coding their application, specify all these things that would determine the behavior of how they ran. And it just got lost, and like, oh my God, it was a great idea. So
I think, but it's ironic because if you look back at those early approaches, they were essentially data driven, right? There were people who were trying to make tables essentially in databases, specifying the data required to configure certain devices, but it was in a data-oriented way. What today we might stuff into just a whole bunch of JSON files, one per device, and it was sort of mass-produced, pushed out to these devices from some central agency, and the amount of data that was involved was pretty huge. And back then, when we only had tens or hundreds of machines, not like tens of thousands or hundreds of thousands like today, it was almost doable. But today, of course, it would be completely out of the question to be able to manage every device with a whole extensive list of data.
Yeah.
And this is where the notion of a DSL, domain-specific language, came in, because you needed to represent patterns to compress that information, those data, into something smaller. And just look at SNMP, for example. There were, because they tried to introduce one MIB for every device, essentially on different versions of different operating systems, different devices, every new thing ended up in a new MIB, essentially, or a new version of this. And something like 120,000 of these MIBs now, of which only about 2,000 are in use, because the others simply fell away. They got deprecated or became disused. Similarly, with the Common Information Model, they tried to do it with relational databases instead of this.
Kind of an object format for the SIM, very similar.
Yeah. But it got lost in exactly the same way. So take, Cisco, for example, who were part of this initiative in the beginning. Anyone that's worked with Cisco devices knows that every single device and every version of the operating system on every single device is slightly different. The commands are a little bit different. They don't fit into a nice, simple model. So the explosion of information, the explosion of data required to do that configuration becomes just, an explosion of semantic complexity.
Yeah, no, I think, and it's interesting as I really did think we were going to talk about DMTF and Common Information Model this morning, which is interesting because I have a lot of background. I think what happened, like, to that point, like, I mean, there's two threads, right? There's kind of the SNMP, there's kind of the SIM model, and you're right, it's this like tree of just object hell, if you will, right? And I've got to get to down here is how I change a user ID. Because the two interesting things there is, one is going back to the AMS. Conceptually, it was brilliant of trying to give people kind of developers semantics on how to kind of intent of operational aspects at runtime. Again, very few people have really done that well right in the developer's face. And by the way, you're the developer. I'm just going to give you kind of these simple semantics. The problem was, to your point, was we didn't even even understand the complexity of how those things were going to evolve, or anyway. But then the other thing is how we solve that is through this kind of kind of DSL, which really took us right back to the program idiom, right? Like as opposed to the operations. But with that said, a couple of things I want to do. I think it was really interesting. I was actually telling somebody your history a little bit the other day, and they're like, "Is that written down anywhere?" I'm like, "Yeah, kind of in this book." But so I've got my background. I've done these kind of things, and then I always tell the story how I sat in an OSCON and I saw Luke Knies give a presentation on Puppet, and I was like, oh my God, everything I've been doing is wrong. And I think in an earlier podcast I learned that Chef and Puppet, they all kind of inherited. But I think your story is cool. You're a physics professor. You wind up being in computer science, and you are then forced to think about generation, or what I call first generation configuration management as a solution to solve a problem. And take it away, Mark.
No, but actually, the thing that got me started on this, I mean, I literally came to this with my hands dirty, setting up Sun workstations back in the day when I was a postdoc at the university. We got some money for a project. We bought a bunch of Sun workstations to do our latexing and whatnot. And because I had an interest in computers, I eventually took over the job of managing these things, which was cool for a while. And then, it becomes less cool when you realize it starts to take over your life at all times of day. But the thing that I observed was, and from my sort of physicsy perspective, was that the whole way that we're taught to set up machines is to start with an initial state, which is you unpack the box, straight out of the box, and then you install some basic image, or it was from tape in those days, the basic operating system, and then you start to configure it or modify it from that point, which is kind of the way, NASA engineers think about sending a space flight to Mars or to Jupiter. They start from some basic trajectory, which is, flying out of the Earth, and then they're correcting it a little bit to the left, a little bit to the right, a series of what we like to call deltas or diffs. And this is, of course, is how people calculate the solutions to equations to solve those trajectories in mechanics, in physics, in Newtonian physics, which, fine, it gets us to Mars with amazing precision, but only by brute force computation of the most terrifying kind. We need computers to do that. But once you've done this a few times, but unpacking a box and trying to remember the exact sequence of trajectory changes that you need to make in various files and in the order in which you need to do them, and if you do one small thing wrong, you find yourself spinning off into a black hole. Mm-hmm. This kind of model of fix the initial state and try to adjust your way to hit the target at the other end. That is actually not a great way of trying to solve the problem of arriving at your destination. And what I observed in myself was that, if we could somehow simply specify the end state, the desired end state, I guess we call it desired state these days, but, if we could simply define that end state and have the system adjust itself to sort of fall into that desired end state all by itself, by designing by the very construction of the system, by creating a configuration system in which it was wired almost to fall into that state, then it would be so much easier, because then you would simply have one piece of information, which is your trajectory, your target, your coordinates, if you like, your GPS coordinates. And then this system, much like a GPS system, would find you the route automatically to get there. And you wouldn't have to be thinking about all these little details. What happens if an asteroid passes me and knocks me off course? Then yes, I need to correct my course again. And I need to do it often enough so that, I'm countering the noise of the environment and so on. So that was the initial thing, to try to move away from fixing the beginning state to fixing the end state.
I was going to say, sorry, so the question begs, so you're a physicist, you have a lot of science. I mean, it's clear when you read your book, right? Like you kind of give examples of Shannon and Parity Bitch and how you arrived. there. Is it so? All right, you got to tell the truth now, Mark. Was it really a pragmatic way? Okay, I'm just going to automate this, but I had a lot of all these kind of concepts in my head, and then it was later, like, because you also, so now, basically you wrote CF Engine 1993 to solve this kind of desired state problem, sounds like, but at some point, either initially or, like you talked about some, and when I want to talk about your computer immunology papers in 1997, where did, because it's clear in the book, like Shannon, and you got all this, we'll get into kind of your next kind of generation of configuration management promise theory, but when did this, because you have some really cool things, like you talk about a statistical equilibrium, and there are two kind of variables of a statistical equilibrium, which is convergence and idempotency. And then, so, and I do have a question about something you said there too. So does that make sense? Yeah.
I mean, the story is very simple. I was sitting under a tree in Cambridge looking at the moon.
Don't say an apple fell on your head, right? Okay, go ahead.
Okay, that was a small fib. Actually, it would have been an apricot before the apple, right?
Okay.
But no, actually, because I suppose because I was a physicist at some level, I had all of this kind of programmed into me at a deep genetic level from many years of working on these things, and so it was sort of intuitive for me. And I'd love to say that I sat down and with my notebook and wrote down the gravitation law like Newton did and plotted the trajectory forwards, but it wasn't like that at all. I just sort of intuitively had in my mind that it had to be something like this and that this would work. And I implemented it and had it working for a number of years before I actually understood what I'd done. So it was more of a Darwinian thing, there was a random mutation on my part. So I was a slug, inching, or an inchworm, inching my way forwards, and it seemed to hit the target. So and then I started to look back and think, how could I formalize this stuff later on? And I realized that actually it embodies a lot of these ideas which I take for granted because they're so part of my cultural heritage, so to speak, whether they come from Shannon or Boltzmann or statistical mechanics or Newton or actually all of the above. And there are elements of all of those things which are related to one another. And which is why I used the term convergence, I think, for my version of this desired end state configuration, rather than a more mathematically computer sciencey word idempotence, which people later used to describe a part of it, because that word was already in use in computer science. So, but I think the intuition of that was somehow ingrained in me from my cultural heritage, and then later on I understood. Actually, almost when I tried to communicate it to other people, I was forced to understand it myself. And I have this story about going to LISA, 1997, the Usenix LISA conference, and and I held a talk about how CF Engine worked in this sort of convergent idempotent way. And a couple of guys came up to me afterwards and said, "Oh, so is this like like a front end to cron or something?" And I thought, well, yes, but maybe that isn't the message I was trying to give.
That's funny.
And then so on the plane going home, actually by accident, I got sick, as you often do when you're traveling, and it occurred to me that perhaps I could use this notion of the immune system repairing your state, repairing your desired end state, maintaining your maintenance, theory of maintenance, essentially. And so I spent the year actually trying to think through a good analogy in terms of immune systems to explain how this desired end state stuff would work. And I presented that paper at LISA the year afterwards. I actually won the best paper award, and afterwards, a guy from a lab in New Mexico came up and asked me if I knew of Stephanie Forrest's group at the University of New Mexico that had a group in computer immune systems for security. So actually, we in parallel had the same idea in completely different contexts. And so we sort of got to know each other a little bit. But to this day, we still work on different aspects of it. But yeah, so this, this I chanced upon it and then quickly tried to make it look as though I knew what I was doing.
But just as you talked about, so you talk about kind of again the statistical equilibrium and convergence, and then at one point, so it just to kind of to tie that back a little bit to just the science, but convergence and idempotency. And the thing I that kind of still I kind of stuck with me, and you say that convergence is idempotency, right? So, and I've always, there's kind of three ways to talk about idempotency, maybe four. You could talk about the pure mathematical thing, and I think then some people get mad that because on one end there's the pure kind of mathematical idempotency. On the far end, it's a script that does a checksum of a SHA, or an MD5, right? Because that's how it's been implemented in most, like, again, not to pick on Schaffer Puppet or anything, but in general, really what idempotency means there is if there's a config file, there's a checksum, and then as it runs, it looks to see if the checksum has been changed, if there's a change in the file.
I think though that people are actually using the terminology wrong. What idempotency means is that if you do something once, so doing it twice is the same as doing it once.
Right.
But that's not the same thing as getting to the right answer. So if you just do something once and then turn off the system, assuming that you've arrived at your desired end state, you're probably making a huge mistake. Because what happens if then later on you find that you've moved away from that desired end state, something has happened? So actually, I often hear when I go around talking to people about configuration management, regardless of what tool they're using, whether it's Puppet, Chef, or CF Engine, many people still have the idea that you only have to configure something once, and then you step away, you leave it alone, and of course, then it's perfect. If you don't touch it, nothing will happen. This, of course, is completely wrong, because there are all kinds of things messing with your system, even if you don't touch it. Programs crash, the network causes things to change, cron jobs are firing off, all kinds of things are going on in a pretty complicated environment. So if you do something once, say like you install a package, and you assume that that package will be correctly installed forevermore, you're making a mistake. So it may be idempotent to say that install package once, if you fire off the command to install the package again, nothing happens. That may work, 2 seconds after you've done it. But a year down the line, when this thing has been broken somehow by outside interference, doing it again may not get you to your desired end state. So it's not converging on the desired end state, even though it's idempotent. So I think this is a crucial difference between convergence and idempotence, is that in convergence, the emphasis is on getting to the right state, not on how many times you have to do it to get there. Does that make sense?
Yeah, no, it does. In fact, I was thinking as, I was trying in defense of things like Chef and Puppet, right? Just not that they need defenders, but I think because I was thinking this too, when I think conceptually when they talk about idempotency, they mean kind of the policy or the semantics are idempotent, right? In other words, that which isn't right in general, but again, baby steps, right? We have nothing as an industry, and then people implement. And so the abstraction is idempotent in that saying that, hey, I'm going to run this every 30 minutes or every hour. And, step one is install the package. Step two is configure a configuration file. Step three is going ahead, or, the primitives inside the DSL. And
right. I mean, what they mean is that when you get to the desired end state, it's idempotent at the desired end state. But it assumes, what they're assuming is that they get to the right state. So in a way, that is what they're saying isn't necessarily wrong, but they're emphasizing the wrong aspect of this in my view, because the important thing is the state and not how many times you have to, perform an operation to get there.
Right. Yeah.
So that's my nitpick, if you like, but I think it's kind of an important nitpick, because if people are just sort of saying the words without understanding the principles, then we're not really making progress on it.
Well, and I guess
And this
that's
has caused that whole, argument about, is a package manager just as good? Why don't you just package things and keep installing packages? And you could say the same thing about the new container story. If you just, do this, do it once and forget about it, throw it over the wall, fire and forget. What do you call it? Immutable infrastructure.
yeah.
People calling it this. If you emphasize this thing that you just have to do it once, then you're kind of getting away from the important aspect of the predictability of the system, which is that you have an intended state. And actually, this intended state may be moving. It may not be a fixed target for the rest of history. You may have new versions of software. You have software updates. You change your mind about security policy and so on. You may be installing new users, granting people access. So there are all kinds of changes going on, and so your desired end state may be moving. What's important is that you have a process which is moving faster than your desire or your intent is moving, which is maintaining your intent faster than your intent is changing. This is the notion. This is what I actually ended up publishing in 2000-ish theory of system administration, which is really a theory of maintenance theorem. It's essentially a version of Shannon's theorem, error correction theorem, which says that if you want to arrive at your correct desired end state, you're basically doing error correction on this changing target, and you need to morph your current configuration into that desired end state on a continuous basis. But by Nyquist's theorem, you have to be going at least twice as fast as any change you're going to make to your intended outcome if you're going to get there without spinning out of control into a black hole.
Well, I guess it doesn't come down to kind of layers then, because again, if I say that I'm going to create an abstraction that says, these are my desired states, and then I'm going to run that every hour, and the devil's in the details, right? But the abstraction is, I want version 1.1.7 of this to be installed. I want this configuration definition to be installed, and I want the kind of service to be set up in this kind of way, right? And then the first time in, it does all that magical stuff. The second time it runs, again, more familiar with Chef than anything else. It basically, is the package installed? Yes, good. So from the policy description, that was idempotent. Like, it ran again. You didn't have to say, oh, don't run this because it's already installed. You're going to reinstall it and all havoc will happen. It's going to be, okay, there is some kind of meta tags or some, in the case of a package, you talk to the package app, the package manager. Yes, it's installed, great. Config file. Last time when I created it, I laid down, kind of a signature, and then I checked the signature the same. Yes, okay, I'm not going to muck with the config file, so on and so forth. Right? So you kind of completely go through. So at the highest level, okay, check mark, that is idempotent, right? But then
Right.
To your point, there's another, like that could be a dangerous way. You didn't say the word dangerous, but at scale, as things can get complicated, there could be a lower level of drift.
All right. So what I try to emphasize to people is that there are really two things going on in this story, not one, and that is there are dynamics and there are semantics. Again, back to this, these two aspects of systems. The dynamical things are the timescales. How often do you do it? How big, an area are you looking at? How big a region are you looking at? Are you looking at a whole package? Are you looking at the details of the package inside the package, or just the whole bulk thing? So the scales are important, both in time and space, if you like, or memory bits. And then there's the semantics. Is it version 1.1.7? Is it version 1.1.8? Am I doing the right things in the right order? So there's your intention. What you're intending is something quite different to how often you need to do work in order to arrive at the implementation of that intention. So semantics, purpose, intent, dynamics, timescales, repetition, these are two different aspects of configuration, both of which are extremely important to arrive at a properly configured functional system. We tend to emphasize the semantic part because that's what computer science traditionally is about. Semantics are what developers think mostly about. We know operations people have to know about the dynamics of systems, and you could, and sometimes I say that dev and ops are almost semantics and dynamics, each their own. It's very simplistic, but we know that those two factions, if you like, often understand the problem more from a semantic view and more from a dynamic view, which is why they often have trouble communicating. And this is exactly why we need the association of dev and ops to understand that thing between them. But the crucial thing, which is really Shannon proved, and and later on I adapted to sysadmin, is that whatever you try to do semantically, it's a waste of time unless you can do it dynamically fast enough and on a big enough scale to be able to cover the dynamical problem. So semantics ride atop dynamics, not the other way around. But very often when we think about systems, we only think about the semantics, and we just assume that the dynamics are either absent or they will take care of themselves somehow. And that's just wrong. And that's essentially where CF Engine made its mark in identifying this distinction between the dynamical processes and the semantic processes.
Was it so? I kind of tell publicly already talked about story related to dynamics, but I think I have a deeper question. So Facebook, publicly switched from CF Engine to Chef, and it was kind of funny because early on, they were talking about how they were going to do it because they had been running CF Engine forever. Right? So these are present. I'm not giving away anything because, in fact, this all happened after I left Chef anyway. So, but they give this presentation about how they run their infrastructure, how they're going to build Chef, and how they're going to do this stuff. And what was like kind of funny actually, which was they had been running CF Engine at the kind of 5-minute interval for forever. And they were, the first rev where I first saw there, we're going to go 100,000 nodes, Chef, and all that. And we think we can get down to, 18 minutes, and then, the next time you see them, like, they've gutted almost all of Chef. They've taken out this, taken out this, taken out this, taken out this, all the internals of how they keep node information, all that stuff. And like, they're down to 7 minutes. And I'm not, I guess where I'm going with the question is, was it that was dynamics, the match of dynamics semantics, was it that CF Engine was very good architecturally at dealing with kind of fast-paced dynamics, or is it was there a lot more under the covers in terms of dynamics?
That's an interesting question. I think CF Engine was fast because it was written in C.
Right. Yeah. And it didn't have a whole lot of. Yeah, it didn't have a whole lot of other things that were built into it. Right.
Very few dependencies. So this is one thing, but also, it had a bunch of optimizations as to how to schedule the things that it was doing. So that was one aspect of it. But I remember this point at which Facebook moved away from what was then CF Engine 2 onto Chef. And what they were being hit with was the data explosion. Again, going back to where we started on the data-oriented management, CMS and SNMP thing. They had so many configuration settings to get through that it was just really hard to maintain the configuration policy. And they found that they could. What they really wanted to do is to have some sort of package manager approach. I remember the guy saying this to me, if we could just somehow make packages, and what he really wanted was containers, of course, but it was a bit too early for that.
Mm-hmm. It's interesting, yeah.
If we could just package software in this simple way without all of the dependency hell that came about from, with the traditional software package managers, this would be a simpler way, because our sysadmins are having to deal with all of these micro settings and data intensive settings. And it's just too much information to understand. What we simply want is to draw a black box around a whole bunch of these settings and say, this type of machine, that type of machine, which is, going back to our earlier podcast, it's a scaling argument. How do we hide detail in a sort of procedural package wrapper? How do we wrap things into a simple name so we only have to know one name instead of knowing all of the little finicky details about how it's made? So yes, this is a radio. It's not a resistor connected to a capacitor with a diode and an inductor and whatever.
Mm-hmm.
And this was really their goal. And they decided that Chef, because Ruby was a nice language which was becoming popular at the time, they decided that they would probably be able to make that vision work with their developers, who were Ruby developers, of course, more easily than trying to hack on CF Engine, because CF Engine was a much more closed architecture. Chef was much more open architecture, much easier to get inside the workings and fiddle with it. CF Engine was a closed architecture. You weren't supposed to go into the details. You're supposed to use the primitives in this purely declarative language. And if you couldn't do it with the declarative language, you couldn't do it, or you had to work around in some complicated way. And I think this was also two things. One is that CF Engine's primitives at the time weren't able to keep up with the challenges that people had in data centers at that scale. And also, programmers are, of course, imperatively trained, that they're not trained to think in terms of desired end states and declarative languages. So they found this notion of declarative programming very hard. What they really wanted was to go back to imperative programming, which, of course, Chef made it easier for them to do. And I think over time, things have slid back more towards the declarative state again, because, again, this is a way of hiding details and eschewing that huge explosion of information, which is the real thing that we struggle the most with. So, when I came to implement CF Engine version 3, I spent a lot of time, and this comes to the development of Promise Theory, of course, but I spent a lot of time trying to understand how to scale the knowledge required to manage all of those fiddly little bits that we have to tweak.
Yeah, no,
because it was a knowledge management problem fundamentally.
Yes. No, it's cool. Again, one of the things I love about going back and reading your book is that I realize how you've always approached the kind of emergent problem of the day through pure science, right? And I don't want to talk more about that. And I think, which is like kind of, we're starting to see some of it now. We talked about this in the early podcast, but what's interesting is, because I think about my days at Chef, right? That was, to a certain extent, one of the reasons that Puppet was created was because Luc Knies kind of felt that there were those kind of things emerging that he needed to create a more declarative way for people to be able to get around the edges. And in fact, what's ironic is, Adam does the same thing. And what does Adam do? He completely punts, right? Because and that is, he just says, you know what, my DLS is going to be Ruby. Just for the people who don't know, Puppet, the DSL was Puppet language. Under the covers was Ruby classes and all that. So and then Chef comes along, and Adam has all these problems, and now he's faced with a tipping point, which is cloud, which is something Luke didn't have to deal with. And Adam is struggling because there's just more and more and more and more and more edge cases. And so Adam says, you know what, I'm just going to flip that the DSL is just Ruby, and then I just add all these classes, which are your simple primitives. And so now you get into a world, at least at that time, where actually selling against Puppet for a lot of reasons, but one of the reasons was that you could say that Puppet is great unless you run into an edge case, and when you do that, let me show you the code that what's going to look like. You're going to have to shell out. You have to write a Ruby class. It's going to be tough. Whereas in Chef, at least the argument was that, like, when the most reasonably hard edge cases can be shimmed in with just inline Ruby code.
And when people tell the story, they often present it as a development of technology, technology getting better or improving. I think what it really tells is a story of a shift of culture.
Yeah.
Because when I see, when I started CF Engine in the 90s, most sysadmins were a fairly stable bunch. I mean, we didn't need that many sysadmins back then. They'd been doing it for years. They're graybeard types. They had deep knowledge of the system. And then there's this huge web explosion came where a lot of new young people were hired who didn't have the long-term experience. They didn't know Unix very well. And they needed to get up to speed, get something figured out fast. And it was easier to use package managers and then change things and write scripts and then program in the languages that they knew because they didn't have that cultural background. So, and even in the transition from CF Engine to where Puppet became popular, I know Luke was frustrated with, because the technology was changing so fast and the challenges we were facing were changing very fast. Luke was sort of frustrated with this idea that CF Engine wasn't adapting fast enough to those challenges. There were in CF Engine 2 back then, and it was sort of limited the kinds of things that you could say or promise. And so he wanted to work. He wanted to reinvent a system, as I recall, more in the image of what system administrators felt was their culture. And if you look at the design of the Puppet language, certainly it has had more cultural resonance with sysadmins than, say, CF Engine did in that time. And then, of course, when Chef came along, he'd already moved on from those days to a more of a cloud environment, as you say, and more web. Now the web is more entrenched, and people know these languages like PHP, Ruby, and are able to use those to solve some of their problems, and they want to continue to use the languages that they know. And because these challenges, again, are moving so fast, trying to create a single tool, a single technology to manage them is also very challenging because the tool has to move as fast as the challenges match. Otherwise, it's not helping you. If it takes you 3 years to learn CF Engine, you're not going to do it because by the time you've learned it, it's already too late. So certainly, just the speed at which things are moving has changed the way that we think about configuration and forced change upon the industry as well. That's not to say that I believe that the approaches that we've developed and the lessons we've learned of configuration management are dead. But certainly, as I give talks now, I emphasize that we need to think more about the timescales.
Yep.
And actually, we need things that we would traditionally lump into one big tool, like, say, CF Engine, like spinning up virtual machines. Back in 2006, I wrote, the early versions of libvirt. When that came out, because I had, my PhD student at the time, Kerry Begnam, was very interested in the cloud. We wrote this version of what I guess something like Kubernetes, but using CF Engine agent running every 5 minutes to spin up and down virtual machines. And he had, my student also had another tool which he wrote himself to do the same thing. And so we were looking for ways to make this problem happen. But of course, CF Engine is the wrong time. It works at the wrong time scale to spin up and down containers. With a virtual machine every 5 minutes, okay, maybe.
Right.
But when it takes a few seconds to spin up a container, waiting for 5 minutes is nonsense. So you need something now to adapt to that change of speed, what your technology is capable of doing, what demand is forcing upon you. You need to be responding to the challenges that are occurring at the right time scale. So whereas before we would lump things into a single time scale, now it's much more important to separate out the time scales, just as we do in operating system design. So, the things that happen at the microsecond scale, the nanosecond scale, in the kernel, in daemons running, in batch jobs running once an hour, once a day. And if we separate out those jobs so that slow things are not holding up fast things, it's a scheduling problem. then we can actually understand the whole of configuration management again in a new way, again separating out dynamics from semantics and making sure that semantics ride on top of dynamics happening at the right timescale.
Yeah, no, I think, again, and I think this is definitely something. I mean, we should definitely attack, kind of the new world of what does CM mean in another podcast. I'd love to do that, but I want to kind of close up on your kind of culture thing again. Example, same thing. Adam spending a lot of time working with Puppet, starting to feel that Puppet is not keeping up with the things he has to do. The culture is, and then as we've discussed, and again, this isn't a hack against or a negative against Chef. It's just a reality. Now, Chef has struggled for many years to keep up with the changes. So the DSL has gotten extremely complex. And then to use a word I learned earlier in our podcast series, there's a form of entropy really on how the semantics describe the dynamics, right? To the point now that in general, at some point the world gets so complicated. And then what is happening, and I don't think it's like, like containers, it wasn't like somebody was sitting there playing with Chef and going, oh my God, I got to do containers. It just kind of came in at a certain time where the complexity of what you had to do with these kind of modern day CM tools became like when this alternative just showed up on the street, it's like, oh, wow. Yeah, I think, what, it's almost like what you're saying, what Facebook wanted, which is, like that stuff's great, but it's like 80,000 miles wide. I'm just going to call this, X. I'm going to call this Y, and I'm going to build it in this kind of container abstraction. And,
I think that the container thing is interesting because it is precisely a scaling argument, trying to black box off details and delegate, the right information to the right people using a human. Interesting, that to solve the automation problem, we go back to handing it back to humans to deal with. That's kind of interesting. But so you also see us tool designers being somewhat naive through history, thinking that we can simplify this problem in the face of a culture of IT, which is basically out of control complexity mongers.
mm-hmm.
Every time one of us tries, so CF Engine was designed around these tiny atomic, very simple things that were provably convergent. Puppet tried to develop some of those things and make it more culturally accessible. Adam developed it around more of the framework, the frame of mind for web developers to understand using that culture of Ruby programming. And then, today with the latest Habitat offering from Chef, I believe, and I'm not putting words into their mouths, but I believe what they see is that, this huge explosion of complexity that people end up putting back into these tools we've tried to keep simple. They can't help themselves from just building layer upon layer of complexity and making it blow up out of control. And so this is an attempt again to sort of dial it back and take out that complexity again. And I'm sure that it's hopeless because people will then abuse these tools as well.
Yeah, that's what happens.
The complexity back in. And I think the problem is a cultural failing in the IT world altogether, computer science world, which is reasoning. We fall back. We believe that reasoning is what lies behind computing. I never believed that. I believed that dynamics, simple dynamics, were an equilibrium where maintenance, if you like, is very simplistic, transactional almost changes were behind the stability and configuration of computing systems. But it's this notion of reasoning. First you do this, then you do this, and then we must have that. And this thing depends on this other thing, which depends on this. And by separating out these concerns into this highly modular structure, we have clearly created a once only fully
isn't that the
normal form ordered relational structure which defines everything once and only once, and we are perfect in our precision. This is what creates complexity.
in search of certainty, right? Right.
Yeah, but
Isn't that the point here, right? That this whole idea that that these things kind of, no matter how hard they try, just keep getting morphed into you start from a deterministic reasoning standpoint, and you're trying to control complexity the wrong way.
yes, I think that's exactly the point. We're always trying to turn a non-deterministic story, which is getting faster and faster, i.e. becoming more and more resource intensive, into a deterministic or a quasi-deterministic story, which means that we have to work faster and faster to maintain it. Just like that, NASA moonshot or Mars shot, which is having to correct its trajectory through all of these little things, knocking it off its path, or the equation solver doing the differential equation, having to correct, doing its time step smaller and smaller, just like Newton did to develop his calculus. You have to make the interval between the corrections smaller and smaller, tending towards zero, in order to make it more and more accurate. Because you have to, the amount of information is sort of tending to infinity as you get more and more precise. But if you step away from that and you take a more statistical approach and recognize and embrace the statistical nature of it, and look at it in terms of matching timescales or matching scales simply. So again, back to the scaling arguments, then I think there are approaches, or what we've sort of proved over the years is that there are approaches to dealing with this which don't involve that infinite amount of hard work, what we'd call vertical scaling today. There are rather horizontal scaling approaches or containerized scaling approaches, or these other approaches which can be used. And if we only understand the principles correctly, we can use them in the right way, and we can make sure that our semantics come out right. And that's sort of where, for me, the promise theory part came into it in CF Engine, when I realized that there was this other aspect to the dynamics which hadn't really been talked about, or we didn't have a proper understanding of, which is intent-based systems, desired end state, how the semantics come in. Well, they come in through some sort of cooperative, then distributed problem, and this is what led to promise theory.
So it looks like we're definitely going to have to do the promise theory on the next one, which would be a great segue. I do have some one question as you were talking that would probably be a complete whole podcast. So I'll ask the question and you give me like the 90,000 foot level of what you think, and then I think that will turn into, depending on what I think your answer is going to be, a whole session itself. And then the other thing, let me do that, and then I'll kind of end on a nice setup for promise theory. So as you were describing that, one of the things I've really become kind of a jack of all trades these days. I don't know if I'm doing myself any service. One day I'm like studying Decker, next day I'm looking at Cynefin, the next day I'm looking at going back and looking at John Boyd. I'm trying to do this kind of compendium on DevOps in a couple of areas. So I'm like just trying to stretch a broad stroke description and even cybernetics is something I've just scratched the surface. I can now walk into an IT party and sound very intelligent, but don't take me deep on any of this.
Are there parties in IT?
I'm always looking for them. I can't find them. But,
partitions. I think you're thinking of partitions.
Yeah, totally. But anyway, so as you're describing what you're describing about this kind of always trying to kind of deterministically, cut the problem in half, going to infinity, right? What are your thoughts? And again, this probably turned a full podcast, but like, is the whole feedback loop thing wrong? The kind of cybernetic, wrong is a strong word, but do you think it's counter to the way you think this thing has to be solved? Like cybernetics and because the only point is that whole idea of kind of, missile, taking a missile and ballistics, a lot of that, the cybernetics was, a big part of that, and even OODA loop, right? Well, OODA to a certain extent, but certainly cybernetics, where you're constantly readjusting to get to the proper target.
Yeah, no, actually, the feedback thing is exactly right. There's in fact, as Jeff Sussner pointed out to me, that much of what I've done, I never knew much about cybernetics until I talked to Jeff. He's a fan of cybernetics. But then I started reading all of the historical books by Wiener and Ashby, and which Jeff recommended to me. I recognize now that a lot of the work that I've done has been to reproduce these ideas of cybernetics, which were developed for the analog machine world. And my take on it has been to sort of almost reinvent that stuff for the digital machine world, the information world. So I think that feedback thing is exactly right. What people get wrong is this difference between fixing the beginning state or the end state. When people try to fix the beginning state, there's no feedback. You're going forwards. You start from a known state, like packing it out of the box, bare metal, and then you proceed in what I sometimes call a ballistic way, which is that you go from one collision to the next, one change to the next, one correction to the next correction, like a game of billiards. And this is sort of the quasi-deterministic ballistic approach. The problem with that is that you never correct. You have to know the precise set of corrections from the start to get you to the end state. And so if you haven't got precisely the right recipe to do that, or the right map, you will stray off course and you'll never hit your target. Whereas if you turn the whole thing around, which is what cybernetics and convergence are trying to do, and say, look, fix the end state, not the start state. You may be starting from anywhere. You may not know even in what state you're starting in. And that's a much more healthy point of view, because trying to pretend that you have perfect control over a system to begin with is just sort of hubris. So rather fix the end state and try to make sure you have a process rather than a sequence of predetermined deltas to arrive at that fixed end state, and have that feedback loop making the constant correction. That's your OODA loop, or your Cynefin four-sector approaches to trying to balance response to the kind of dynamics that are going on in the system. I think what all of those cases that you mentioned, what they're all trying to say is the same thing that I'm trying to say, which is that semantics really build on top of dynamics. And so you better get your dynamics right to begin with, or understand them, if you're going to have any hope of implementing the semantics that you're starting out with. So that's really, and for me, that was the point at which I moved from this notion of convergence and the feedback loop over into promise theory, which was trying to understand not only are we going to hit a target, but what precisely is the meaning of that target, the interpretation of that target. How do we know that even if we hit that target, it will have the functional behavior that we require in order to solve a particular problem?
Yeah, and I think the cliffhanger for the next podcast is that the target itself has to define the semantics. Again, I think I got it right. The semantics say what the kind of intent is from the human perspective. In promise theory, the dynamics are, hey, I'm going to try to keep to that state, because any other way is kind of folly, right? It's an obligation model of, my intent says you must look like this, but I have no clue what you're doing or any insight of, I'm just going to brute force you that way, as opposed to, okay, I got it, bud. You want me to look like this, like I'm going to do everything in my power to try.
Coming back to the point we just made earlier about reasoning, another way of saying it is that reasoning is the bottleneck. So you try to keep reasoning out of the problem. Try to start out with a reproducible set of states, these desired end states, and build your story of semantics, your functional story on top of these states. It's a much simpler problem than basing it on a whole bunch of processes, which have to be done in a certain order with a certain, success rate, and if they don't succeed at the right times, then the whole thing is fragile. If you base your story on states rather than chains of reasoning, it will be much more stable, or you have at least a chance of making it stable.
It sounds like, to go real meta here, right? Like Promise Theory has been awesome. We do know, even based on what we talk about this podcast, that IT is getting just, well, we're going into kind of is probably can't even say this statement, exponential complexity, but the point is that I think you said something earlier too about like a lot of your time, almost since I've met you, but within the last 2 or 3 years, you think a lot about kind of knowledge management and information in terms of semantics. And if I think if there's a Rosetta Stone at some point, right, it's some better way to encapsulate knowledge and semantics around what we've talked about in the earlier, which are these kind of what were the kind of variables that don't change at scale.
Yeah, we spend an awful lot of time hoping for the best when it comes to semantics. It's ironic that one of the things we understand the least well in IT is the notion of knowledge and intent, how we represent it, what it means, how it's stable, what we're really trying to do. We're quite good at chaining together sequences of actions to make little bits of machinery. It's kind of what software is. But then we realize that we haven't captured the whole story of the knowledge, or we haven't adapted to the changeable aspects of the variability of it. And so we end up with this thing we call bugs. And this, of course, is why you need something like, Humble and Farley continuous delivery model, which is basically an OODA loop again, a feedback loop at a bigger scale,
right?
Continuously correcting, sort of trying to do this real-time error correction and error correction, and only on the semantic level of programs, because we don't actually have a clear way of talking about or keeping track of the knowledge and semantics of things. And it's a challenge, because we want a story which is general enough to apply to either humans or machines, because it's not just computer systems. What we really deal with is human computer systems. Humans are a central part of the system. But it also needs to be specific enough to talk about the interactions between them. So between the machines and the machines, between the humans and the machines. It has to be impartial enough to be amenable to some kind of reasoning, without getting into free will and so on. But it needs to be locked down enough to be able to automate it, to take out the need for humans to be continuously changing or overseeing and adapting the semantics, because humans, all intent arrives from humans to begin with, and the ultimate arbiters of intent and meaning are the receivers of information.
Mm-hmm.
And somebody may intend one thing, but it's the person that receives that thing that decides what they believe it means ultimately. We cannot impose our intent on other people. We can try, but it doesn't, it may not be reliable. So ultimately, people will believe what they believe from things that they see. Unless we build systems around that observation, which is what Promise Theory is about, we'll never be able to build systems that behave in the way that people expect, because the origin of intent starts in a different place to the place at which intent is actually arbitrated, where people actually believe that they are, understand what they're seeing. So it's this mismatch between what was offered and what was received that is behind a lot of the misunderstandings and complexities that arise.
Yeah, no, I mean, we will have a whole conversation about AI at some point, right? Where it even gets worse, right? But yeah, I mean, that's like my kind of, as I kind of start getting all giddy-eyed here about like this kind of Rosetta Stone, if you will. Not that we're gonna do it, but like the dynamics, right? We've discussed the problems. You got the scale problems, right? And then you got this kind of simplistic semantic or intent to say, I'm going to do this, but maybe at some point it's just the complexity is too wide for you. The impedance mismatch is too great. Like I'll give you an example. I'm going to definitely go over, right? So I've been looking at Kinevin. We talked about it a couple of times, and the one thing on one hand, I like Kinevin because, all right, like you're dealing with complexity. First off, it forces you to understand modality of complexity, right? So like right there, it's okay. Like if you don't, if you're just going into every battle with with a stick and a knife and a rock, right, and you don't even really understand the game you're in. We were talking about Guns, Germs, and Steel, like Pizarro and the. Anyway, now I'm going way off the reservation. We're going to talk about Guns, Germs, and Steel, but Jared Diamond. But like you, and so what Kinevin does is says, okay, wait a minute, calm down, everybody. Let me force you to understand there's kind of an obvious mode, there's a complicated mode, there's a complexity, and there's a chaotic. And then I'm going to give you kind of some simple rules of thumbs of how to react. And like, okay, well, that to the uninformed or the people who show up with, sticks and rocks against, galvanized steel blade swords that, to again go to the Pizarro Guns, Germs, and Steel reference. Okay, at least it puts you in a framework, so you could look at it and say, oh, you know what, those guys with the rocks probably ought to hit those guys on the left, But and then I asked John Osbar, right? I'm a big fan of John, and John's done his thesis paper on a, anomaly response, and he gave a presentation at QCon, and I asked him what he thought about Kinevin, and he said, almost like, hey, dummy, didn't you just watch my? John is very respectful and a good man, but almost like, no, I want to get away from abstractions, right? So we're in this constant. So John's theory is that web-facing, scalable web-facing anomaly incident response is so complex, and then and he talks about some of the work that Dr. Woods has done, which is really kind of just intertwined feedback loops. But I guess not to go over too long on this podcast, but there's got to be this mix between getting the right mixture of semantics that can adjust to the as we've talked about, the scale that we have to deal with, and and be able to get that right, and then in a world that's ever changing and with the absolute paradoxes, it's never going to be right, because humans and complexity, almost like the airline pilot, right? The airline pilot, like the semantics of flying a plane are way different today than it was 30 or 40 years ago.
Right.
I don't know.
Yeah, I mean, going back to our earlier podcast, it may be possible to control the weather in principle. It may be possible to respond to incidents fast enough. It depends on your technology. We may be far away from having a technology which makes it possible, and it may be that the presence of humans in that technological mix is either an advantage or a disadvantage, depending on exactly what they're being asked to do. Given our capabilities and given the capabilities of the technologies themselves, these are very difficult questions to answer, and I think it's impossible to answer them equivocally by saying that it's such and such is possible or impossible. It's all a question of do we have the economics in hand to be able to match the cost of putting in the amount of work or the amount of information at the right rate, at the right speed, to be able to make it plausible or not? And that's the open question. And I think the people who make the decisions, the hard decisions about choosing a particular type of system, design, or technology, or even whether we're allowed to do X or not, they have to make those trade-offs and make judgment calls about, do we think it's safe? Ultimately, some sort of moral, ethical judgment comes into the picture about whether we believe this approach is safe in some sense and we need to define that sense, to allow this to be taken over by a human, or to allow this to be handled by a machine. It's hard to say which would be better or worse, because they have very different capabilities, very different properties. So it's dynamic. The dynamics of it, or the economics of it, are relatively straightforward. We can just calculate the numbers and match them and make a judgment. But the semantics of it, and then beyond almost the semantics, the ethics of it become the factor which becomes the thing of central importance, I think.
Yeah, no, and I think I don't think there's a phrase that ever gets used, but economical ethics, right?
Right.
Which goes back to like we know we can semantically push something. Anyway, it just again, my mind is always spinning in these these sessions that we have. It seems like there's got to be some consistent statistical, like you said, way to get to a place that solves more problems than it is, that bridges the divide between dynamics and semantics in a consistent, at any scale, right? Or
and that you just described the topic of the book, In Search of Certainty. That's literally what it's trying to say. That if that thing is possible, then this is how we go about answering that question, how we go about doing it. And it doesn't say that it is or it isn't possible, because that's
right.
a circumstantial question, but it does show you how to address the problem in a scientific way, rather than a fluffy sort of hand-wavy way. I think that's the important thing, right? So because a lot of the skills associated with making those determinations are absent from computer science, we've been weak in addressing those issues in computer science. Other aspects of science and engineering have been much stronger, because they have different backgrounds with some more of those skills, perhaps. So part of what I'm trying to do is to bridge some of those cultural gaps and bring some of those techniques into the mix of computer science in a way that hopefully is intuitive and will be able to be used.
It's hard. It is hard, because this is kind of how I'll end this podcast, as a kind of cliffhanger for the next one. We'll definitely go into promise theory next time. Again, as I read the book, and I compliment you a lot, but I only compliment where I think it's worthy, and it is that the fact that it is clear that your body of scientific knowledge has always played in everything you've tried to solve in this industry. And but it's hard for people like me and other people who aren't really scientists. I mean, that's why I love being on this podcast, because I get to learn the connections of people. But that I think that's the other part, and I don't think as many people have this kind of pull out of your hat, Shannon, and then pull out of your hat. Like, here's the final cliffhanger. As I was reading one of your chapters of how you kind of got into thinking about promise theory, I had forgotten completely the first time I read the book that you talk about. You even used Dunbar as part of how you thought about it, which is like, golly God, it's so awesome. You got Turing, Dunbar, Chomsky, and I want to get into that next time. But I mean, it takes somebody that is kind of a pure scientist to be in our industry to get us kind of in. I think maybe some of these other. It's funny. I always say this, and there's another video I watched by this Alan Kay, and I think we talked about this early. He shows like three famous, Galileo or Newton, and he asks everybody who there is. Then he shows like 3 or 4 famous computer scientists in a computer science curriculum at a university in Illinois, and nobody knows who they are. And so we really should, like, some god of like naming stuff should come in and say, thou shall not use the phrase computer science anymore until you can get to this level, because it in a lot of sense, and no disrespect to the smart people who do things at Google and all that stuff, but as an industry, it's kind of a joke to call it computer science.
I don't think it's impossible to reach that point. I mean, I've been motivated by the fact that there definitely a science around computing. And one of the reasons for writing the book was to point out its scientific heritage. It's just that we don't talk about it and people don't learn it because it's very much can we solve this semantic problem? Can we write this computer program? Is how we've ended up talking about computer science today. I mean, it wasn't always that way. And back in the 60s and the 70s, people who called themselves computer scientists would have been much more appreciative of those aspects that I harp on about today than they are today. But in a way, it's a failure of it's a knowledge management problem again. One of the many knowledge management problems that we face.
Well, and then like one last thing I always say is, but how could we survive when the first thing they try to teach you in university is compile design, right? Like, right. So talk about, semantics. All right. I think we've definitely gone way over, but I think I had fun. So
this was good. Yeah. Thanks once again. And next time we'll do Promise Theory then.
And looking for feedback, folks. I mean, again, go ahead. Like, if you think what we're saying is stupid, or you think you want to add on, we definitely, it'd be a lot of fun to just get more feedback in every couple of podcasts. Just kind of answer the questions, and if at some point you want to be on the show, give us a holler. We'll get in. We'll muck it up, man. Muck it up on the science stuff. Anyway, thanks, Mark.
Cheers, John. Bye, everybody.
Yeah.